Welcome back. We're going to wrap up section 1.2 and section 1.3. So that's scientific experiments and scientific theories. So starting off, I want to quick go over the data types. All right, there's two basic ways that you can get data. The first way is quantitative. It sounds like it's fancy, but really all quantitative means is that we're going to get data and we're going to do it by using numbers. So we're going to say something like, how tall are you? And we're not going to say something qualitative, all right, because qualitative is going to be descriptive. So if I'm asking you for a descriptive version of how tall you are, you might say real tall, or real short, or medium. But that's not something that's always the same. You could have someone who's 4'6" that says, yeah, 5 foot's real tall. And so what we try to do is we try to focus on quantitative more than qualitative, because this one's more consistent. Where instead of saying tall, we might say that you're 6 feet 0 inches. All right? So this is ultimately going to be an actual number now that we can compare. Or we could say something to the effect of you are 72 inches tall. I guess I can put inches instead of the things there. Or we could go through and say that something was 2.3 meters if we use metric like we typically will when we're doing science. That's the unit that most scientists will use is whatever metric form, so meters, kilograms, etc. So we try and shy away from descriptive stuff, which would be like, big, small. You could even, some stuff, sometimes we will use qualitative. And a lot of times when we do use qualitative, it's because it's something that's hard to describe elsewise. So we might say something like orange, which is still qualitative, but it's pretty good, so we don't have to worry too much. But I don't know that we do a whole bunch of stuff with that, but it's still useful in many cases. But we'd much rather go by something as far as size. So if you're trying to figure out what type of animal it is, brown's only going to get you so far. But if you know the exact size and the arrangement of the paw prints, you can probably do a lot better job with it if you have that info. So bubble size, just to give an example again, you could have where it's essentially large, medium, or small would all be examples if we're doing qualitative. And for quantitative would be more like 1 centimeter, or it could be like, half a centimeter. Or if you really like inches, we could say, 1 inch. But it's going to have a number that's easy for other scientists to check you, to verify, and get the exact same answer if what you did was right, or get a different one and know it if you were wrong. Now, once we get all these numbers, scientists hate just a whole wall of numbers. So we want to come up with some way to organize it, and we do that with a graph. And the most common way to do this is you're going to take your independent variable, right, an IV, and we're going to put that off on the left. So this is what we changed. So we changed the level of something, and then in response, we're going to measure some stuff, and you typically are going to measure it at multiple times, because we want to repeat this to make sure that it's consistent. So our dependent variable will typically go over to the right. And so we would fill in what we measured here, and you'll notice that we put the units so we know what we're doing. We list what we're measuring because we want to make sure people know that, like in our one example, this could be cups of coffee. So that would be essentially our unit, like per day, cups of coffee per day would be our unit as well as what we changed. So that kind of takes care of this independent variable and unit. And then the dependent variable over here would be lifespan. And so we could, write lifespan. And in this case, it would be in years. And we oftentimes put that in parentheses as our unit. And so we would go through and mark up what data we got to get our ultimate response. Now, having a data table is great, but most people still look at that and say, that's a lot of numbers. I don't want to look at all those numbers. So they're going to want to do something like a graph, because a graph is a way of taking all those numbers and making them easy to look at, easy to see patterns in, easy to process. And so they're going to go through and they are going to make some basic axes. So if you guys remember, the y is the vertical one, the x-axis is the bottom one. And so what we're going to do is we're going to put the independent variable on the bottom and the dependent variable on the side. And so in this case, the dependent variable in our example was lifespan. So we would write that there so they know. And in parentheses, I'll put years so we know the unit. And then over here, we would put cups of coffee. Apparently put it very close together. per day. And so that would be our independent variable as well as our unit, so we know exactly what we changed. We changed the amount that they got to drink per day. And so down here it could be stuff like 0 at the origin, that start, and so it could be 1, 2, etc., and then we'd fill in our data. I remember which one goes where is that independent is a bigger word than dependent, and so bigger things tend to sink in my mind, and so I make sure I put the bigger guy on the bottom. Independent goes on the bottom, dependent goes on the side. Okay, once we have this, just a quick rehash. When we have these variables, we can then graph our data, and the nice thing about that, like I said, is maybe your data keeps getting bigger and bigger, but all you see is the numbers go up. So you might not realize that what's actually going on is you have like a steep rise, and then maybe at some point it starts to taper off and slowly rise, you know, and then eventually at some point maybe it starts to kind of go up again, but not as fast as it did. And so when you look at the sheet of paper, you just see like this wall of things that gradually get a bit bigger. And so you just go, oh, they got bigger. But when you look at this, you can see the patterns where it got big rapidly, then slowly, then kind of in the middle there. You could make this quantitative by actually doing the slope, so you could essentially figure out how fast it's rising at each of these sections. But for us, just I want you to realize that you can see these patterns that otherwise are harder to like peel out. And so that's why pretty much any lab report that a scientist does will have a data table, so it's easy to see all the numbers they had, and then a graph, which is what most scientists will look right at because it's just so easy to read. If they look at the graph and find something that they think is weird, they'd go check the data table to see if somebody was tampering with their data a little bit to make it work the way they wanted it to, which even scientists will do sometimes, especially if they're being paid by somebody to do the study. There are some of them that will try and figure out ways to kind of tweak things. But luckily, we can look at their work, figure that out, and we can essentially throw them out of the profession for not doing things properly. Now the last bit we have, and this is basically section 1.3 that's in your book, Scientific Theory. And the reason we're having this is because most people don't understand what theory means scientifically. Because in everyday language, people say theory when what they really mean when they say theory is they mean idea. You know, they say like, well, I've got this theory that ultimately there is a bunch of chemicals that are in the water, and when you drink them, it makes you docile. But they've got no evidence to support that. They've no experiments to support that. There's nothing there that even say that that's potentially legitimate. Depending on if they can actually check that or not, if they can actually test it, it may be a hypothesis. But it's certainly not going to be a theory. Because to become a scientific theory, let me cross this out to show it's not just an idea, even though a lot of people say it is. To become a scientific theory, you have to first of all be an explanation of something. All right? So there has to be some natural phenomena. It could be why things fall back to the earth when you throw them up. It could be how you get sick. There's lots of things that we can look at that are natural phenomena, and we're trying to explain why what happens happens. And for this to be elevated to a theory versus a hypothesis that has some support, it has to be very supported by a bunch of diverse experiments that have been checked themselves by multiple scientists over a fairly extensive period of time before they'd ever graduate to what we'd call a scientific theory. There just aren't that many scientific theories that are out there. You know, we'll have 3 big ones that we cover in biology. Germ theory, we'll talk about some, the idea of how you get sick. You know, you get a bacteria, it reproduces, you then sneeze and whatever else and shoot that out. So you can think about that when someone sneezes around you, and then that gets on them, it gets into their system as they breathe, gets in their lungs, and now they can get sick. And the theory is that we can then isolate that same bacteria that you had that made you sick from the next person that gets sick to show that that's the thing that's causing it in the other person. But there's this transmission of this bacteria or virus that leads to disease. And then the cell theory is that all things that are life basically are made of cells. You know, so that we're a bunch of cells. Bacteria, which are like some of the simplest living things, are just made of one cell. But that's the idea of the cell theory. We'll get more into that later. There's more to it, but that's the general gist. And then evolution via natural selection attempts to explain the facts of evolution we see, which are just that things change over time. And so we then have to explain why would things change over time? You know, why is it that something might get bigger or smaller? And so that's where natural selection comes in, where this basically just revolves around the fact that organisms want two basic things. They want survival and they want sex. So this obviously is for sexually reproducing organisms. I suppose if you're asexual, you probably don't want that much sex. But these are the two things that they're driving for. And certain individuals do a better job of both of these, and so they pass on their genes more, and so their particular traits, their particular genes become more common. That's it. So that'll be the evolution via natural selection theory. And so these are three of the big ones. There's certainly others that are out there, like in physics, you have gravity. But when we say theory, this means something as close as scientists are willing to say to truth. Because even theories, even scientific theories, are open to revision. So what this means is that if we get new evidence, we can ultimately change the theory. Now, with most of our more modern theories, what we've ended up doing is just tweaking them because we find new evidence that lets us realize that it's a little off. So it's kind of like when you have that recipe and you realize that if you add more chocolate chips, it'll be an even better chocolate chip cookie. But you're not changing the whole recipe from scratch. Whereas especially a long time ago, although it could still happen today theoretically, is that you could just pitch the whole thing. If you find something is just outright wrong, scientists pitch it. Science is about being right based upon the evidence. It's not based upon you like this theory, so therefore it must be true. So if you can demonstrate that a scientific theory, even this big, well-supported scientific theory, if you can demonstrate that there is evidence out there that concretely and scientifically shows that it's wrong, you pitch it. So this has happened a lot in the past. I can't say as far as recent stuff, I'm sure there's things that have happened, but I can't come up with some off the top of my head. But if you go back in time, there was stuff like Lamarckism, which was a predecessor to evolution by natural selection, which was thrown out because it was demonstrated to be wrong. Lamarck thought that things that you acquired in your lifetimes, like a tattoo, could essentially pass on, or intelligence, or stretching your neck. And so we can prove that no, that doesn't work. You can't dye yourself blue and make Smurf babies. It's not going to happen. You can't pass on traits that you've acquired, is what we call that. So there have been things that were theories at the time that have been pitched. It's just that nowadays we have so much more evidence and so many more people testing it that most of the things that we have now that have survived have been fairly solid. They've been tweaked sometimes, but I can't think of many of them or any of them that are really recent that have been thrown out. If somebody can, feel free to let me know. That'd be cool. Otherwise, that's pretty much it. So we're set with 1.1, 1.2, and 1.3 at this point. Make sure you study the stuff. Make sure you're comfortable with it. Ask me questions if you have them. And I will see you guys tomorrow.